So we now have Jack Jansen, who is also one of the co-authors of Python and which other language was it?
Python.
Yeah.
And Smile.
Oh, okay. Okay, and Smile, and who'll be talking to us about appliances and collaboration to collaborate in the Internet of Things, the Restful. Sorry, I'm mangling your title here, Jay. So I'll leave it to you,
No,
Jack.
because I've actually mangled it myself. Because here it says Igor and Iotsa creating appliances for, and here it says something completely different. He says an architecture.
And who is Igor and why?
And Igor, okay, yeah. So Igor is who has read Discworld by Terry Pratchett? Yeah, okay, a few. So Igor is the butler in Discworld, or there are actually a lot of Igors because they're sort of Frankenstein monsters and they're interchangeable. They're a tribe of people that live far out in the distance and they're butlers. And the Igors are the Igor works for their boss and for nobody else. And so the idea of behind Igor, the name, is that it is a very traditional butler. He knows how everything works in the house, but he keeps absolutely shut about anything to people that are not supposed to know it. What I'm going to talk about is is it not on? Oh, I need to shout harder, or I need to put it elsewhere?
Put it in the middle, maybe.
Put it in the middle. Yeah, it'll ruin the design on my T-shirt, but it's actually the back is better. But but I'd look silly talking to you with my back to the audience. Actually, this is probably going to be the most geeky bit of the presentations that we do. So I'm going to try and do it in a bit of an advertisement style and not become too geeky and just show what you can do with Iotsa. Iotsa is an architecture for wireless sensors and actuators. So what is it? It's part of the Internet of Things. It's intended to be part of the Internet of Things. It is no, that's Igor. Can you see it? Iotsa, sorry, I keep mixing up the names. So it is an Internet of Things server architecture, I think. I've also called it an inexpensive, open thing for small appliances. It's pick your favorite acronym. It is tiny, it is cheap, it is hackable, and it's internet connected. It's what you see here is the hardware. There is a software architecture that goes with it. The idea is that the hardware is easy to modify. I don't know if you can see it, but there's a whole section here that has nothing on it. So if you have a few components, you can solder them on here and then connect them to the rest, and then you connect some device to the internet. The software is very similar. It's programmable with the Arduino. Who knows Arduinos? Yeah. Oh, okay. It's got Wi-Fi, it's cheap. I said all that. Here's an example device. This is a clock. It's fully programmable. If you want different colors for the hands, you can program that. It's internet connected, so it synchronizes the time over the net. You can program alerts into it that you send in the signal, and then it shows some sort of an alert. You have mail, you have a Facebook mention, whatever you want. It's got a few. The inner ring can be programmed as a status ring, so that if something is wrong in the house, as determined by Igor, a little orange ring will show up in the middle. Of course, Murphy's Law said that the last week it hasn't rained in Amsterdam, because actually the outer ring shows the rain forecast for Amsterdam for the coming hour. So that is again the combination with a Iotsa-based clock and Igor. Igor gets the rain forecast from a service on the internet, divides that into 5-minute periods for the coming hour. Igor then instructs the Iotsa clock to show those rain forecast numbers on the outer ring. So by itself, this is just a clock. If it has internet, it'll actually show the right time because it'll synchronize time over the internet. And you know, if Igor is available, then it can do more things. But first and foremost is a clock. Another example Iotsa device is this is a door opener, and my esteemed colleague Sergio will now open the door. So that's an RFID reader with an RFID key. That's Igor, that's Iotsa, and that's the door opener. This thing works in isolation. We've programmed the keys from everyone in our group so that they can open the doors. Other keys can't open the doors. You can add keys, remove keys. You may be able to see, no, not anymore. There's an add key MasterCard and a remove key MasterCard by which you can add and remove keys that open the door or not. If it is internet connected, you can send out a signal that, for example, when I open the door, those specific lights go on in the room. When somebody else opens the door, other specific lights go on, music starts playing, whatever you want.
I think we should also say that people could choose what they use as a key.
Oh yeah, people should. So it's a standard RFID reader. So we use our CWI keys, which happens to be RFIDs. But if you want to use your Oyster card, it works just as well. It's any RFID device will work with this. This is a plant that you can move up and down under program control. It's another Igor device. We'll see a few more. I said I'm going to do sort of an advertisement talk. So I'll now just take you from idea to development to deployment with a Iotsa device to give you an idea of what you can do with these things. So as I said, it's open hardware. I designed this board, but you can download it off the net. We can do whoever wants it can have this one afterwards, or we can organize a fight for it. I can throw it, yeah, but it'll break, yeah. I'll just leave it here and it'll disappear of its own accord. Open software, Iotsa is the general URL for the project. It links to Igor and back. And the example that I'm going to talk about is the Iotsa motor server, is the plant you just saw. So as a case study, wouldn't it be cool to have a plant that can move up and down? Who wants a plant that can move up and down? 2.5, 3.5, 4. Okay, my colleagues, someone I know, and I think someone over there. Okay, that's funny. I thought everybody wanted a moving plant. But let's just assume, for the sake of argument, that you want a moving plant. You think that would be very cool. So now, what do you need? Well, you need the Iotsa board. What is the Iotsa board? It's a small CPU. More serious than an Arduino, less serious than a Raspberry Pi Zero. You need a power supply. This doesn't come with a power supply. It needs a power supply. You've got the experimentation area, and you've got the multicolor LED that you could program as an indicator LED. For example, in the door, we program that red. It flashes red if you don't get access, and green if you do get access. If you don't want the LED, you rip it off. If you need less of an experimentation area, you cut it off, and you have a smaller board, and it still works. Next thing you need to do is you need to design your hardware. So what do you need for moving a plant? Well, you need a stepper motor, and you need that UL whatever chip that controls the stepper motor. You need a micro switch when the plant is fully retracted, so that you don't sort of pull the plant through the enclosure. You need to think of how am I going to build the mechanics, not for this device, but for some devices you've got to think about what is the interactions that I want with the device, housing, etc. Next step is you need to construct it. Well, so you need to solder the components to the board. You can probably just about see that this is actually, they're soldered on in exactly the same way as you saw in the previous diagram. You need to print the mechanics, or otherwise, you know, construct them from wood or whatever your favorite tool is. You need to solder them all together. That me? stand very still. Now you need to program the software in the device. It's now off. Okay. Now you need to program the software in the device. You do that using the standard Arduino IDE, and it's got the, for people who have used Arduino, it's got the standard setup and loop paradigm, where in setup you initialize your hardware, and in loop you do something that you want to do repeatedly. Initialize your stepper position, hardware in setup, move to the required position in loop, and then the only thing that is special about Iotsa is that you have a handler method where you get a variable over the internet, store that locally, and then next time in your loop, that is where you're going to move the plant to. Next step is that Iotsa has a whole lot of standard modules that you can add to your appliance. Time sync, which is using the clock, over-the-air programming, so that if it turns out there's a bug in your program or you want extra functionality, you don't have to take the whole thing apart and connect it to a computer, but you can just program it over Wi-Fi. You may want username password so that other people can't move your plant, or other people on the local net can't move your plant or make your clock flash or whatever. There's a lot of optional modules. You just add them by basically adding one line. By basically adding one line.
Would like to move your plant.
Why does everybody want to? You don't ever want to. I continually want to move people's plants. Now so after you've done all that, if you do an Arduino-based solution, you need to plug it into USB, have a computer closed, all very complicated. The nice thing about Iotsa is that after this, your plant is on Wi-Fi. So that basically means if you go to plant.local/stepper/0 position equals 400, the plant moves 400 millimeters down. And the reverse, you can just ask, where is it at the moment? And it'll tell you I'm at 470, I'm going to 500, my speed is 2.92, and I'm in range, so I haven't hit the switch. So that is very nice, because that allows us to program the actual thing that we want to do, namely let the plant react to something in the environment. And we can do that in any language that we want, and we don't need funny hardware to connect to the plant or whatever. It's just standard internet programming, so it's 2 lines of Python, but then almost everything is 2 lines of Python. But you can do it in Node.js or processing or shell script or whatever your favorite language is. Most languages will have a way to access web URLs, and then you can program your Iotsa device. No wires, no cloud. That's important. So that is back to Stephen's thing about privacy. There is, if you want to use the cloud, you can, but you don't have to. That means it's not that your plant height gets sent to Google, who can then use it for advertising purposes. If you want to send it to Google, by all means, but you don't have to. So Igor Integration. Now, of course, here is where the next small movie should come in. But yesterday, when I wanted to make the movie, the whole system didn't work. So, unfortunately, you'll have to do it with my talk. But what I have at home is I have a Iotsa-based sensor that is connected to my smart meter, my electricity meter. Those are standardized in the Netherlands, so I've built a small Iotsa board that interfaces to those. And basically, it means that my current electricity and gas consumption and historic data and whatever is always available on the local net. Actuator is the Iotsa plant mover, and there is one rule in Igor that says take electricity consumption, divide by kilowatts, multiply by meters, and send to the plant. So I've got the plant at home that, except yesterday, moves up and down as I turn the vacuum cleaner on or off. And that's actually very nice, because that is a way to visualize your electricity consumption without actually visualizing it. It's just a plant, and a fake plant at that, But it's just a plan. But you do notice at some point, you get used to it. So you sort of walk into the house and you say, what's taking up that electricity at the moment? And you go around the house and you see that you left something on, or this or that device uses much more electricity than you expected. That is sort of to whet your appetite. That is the type of things that you can build with Iotsa. Deployment. Yeah, sorry. Important. You've built this plant or this clock or whatever, and now of course you want to give it away to people, sell it, whatever. It needs to be usable. So installing the application can be done over the air or programming through wire. Doesn't have to be. If you need to reprogram it, you can do it over the air. A new device will create a personal hotspot, basically. You connect to it with your phone or any other internet-capable device. You give it your Wi-Fi name and password. It then connects to the Wi-Fi, and it's now online. So they're easy to deploy. And in the security, the security aspects that Stephen mentioned, anything that is potentially dangerous is a two-phase process. First, you need to access the device over Wi-Fi and say, I want to reprogram you. Then you need to go to the device and power cycle it within like 2 minutes, and only then will it become reprogrammable for another 2 minutes. So that basically means that somebody who hacks into your Wi-Fi network cannot steal your clock or your plant, or use your plant to hack into your other devices, unless they can also pull the plug on the thing. And it also means that the cleaner or your visitors, they can physically steal the device, but they can't hack the device because they have access. They may have access to the physical plug to power cycle it, but they don't have access over the net to actually tell the device that you want to reprogram it. So that's the type of things that we're thinking of for doing security. So over-the-air programming, changing Wi-Fi parameters, usernames, passwords, that's the type of things that are sort of built in as security operations. But actually the creator of the software in this device gets to decide what is considered a potentially dangerous operation. Almost last slide. Pros and cons. Truth in advertising. REST services in no cloud. The big advantage is privacy and independence of the net. The down point is that I can't access my plant from here unless I take special measures to do holes in my firewall and whatever. Wi-Fi. Plus side is easy integration. Any programming language goes. That is all very nice. The very serious downside is you can't run off batteries. Whatever I do, if I run these off batteries, if I'm very lucky, I get 24 hours out of a set of AAA batteries with this architecture. So that's really a downside. So it's for the plant it doesn't matter because the motor is going to take so much energy anyway, and same for the clock. It's going to take so much energy anyway that you want them plugged in. But for devices that you would want to be wearable or something, this is not a good solution. And state-based and not event-based or streaming is an advantage for some things, a disadvantage for other things. It sort of depends on your application. Future plans. If somebody wants to market the Neo clock, make a beautiful brushed steel frame, whatever, you can just grab it off the, you can grab the designs off the net, or you can ask me, I will gladly help you. I'd love to do something with that. I think it's a neat device. It could be marketable, but I'm not going to do it. We need a better UI for the web interface. We need deployment apps, stuff like that to make it more usable. Next one's more important. I'm looking at a newer chip so that I can also do Bluetooth LE or mixed mode Wi-Fi and Bluetooth LE, and that may lead to lower power modes. and maybe even lead to something that can operate on coin cells and only once in a blue moon connect with Wi-Fi, for example, to dump all its data or something like that. And that'll sort of lead to, well, we'll hear what Sergio's going to say shortly, but I want to converge, I hope to converge the state-based REST architecture of these devices with the more low-power streaming things that we are going to need in wearables, because this is not very suitable for wearables at the moment. Yeah, I think I said all that. Yeah, and thank you very much.